Hi. In the last video, I emulated the register module. Ran into a couple of issues and got those solved. But today I want to take that register module emulator code and convert that into KiCad schematics. Time permitting, we'll get into a couple of other things. Let's get into it. Hi, I'm Adam. I'm still building a 16-bit computer from scratch. I'm no expert here. I make lots of mistakes. So many mistakes, I've actually had to reboot my computer build. I hope you will find my journey interesting, and I hope you will join me as I learn along the way.
I took care of most of this schematic while I was on a plane, so it didn't take too long, but I'm going to go ahead and fast forward through a lot of that just so it gets done quickly. The first order of business is to place all the components into the schematic. I did all the ICs, however I neglected to put in the line drivers for the control LEDs right out of the chute. I add those later. There are also several logic components, NAND gates, and inverters which need to be added. Next up are the LEDs and resistors. As I'm going through this, you'll see that I use copy and paste quite a bit. And then the connector pins that form the I/O in and out of the module. Finally, the decoupling capacitors I need. The first thing to hook up are the counter ICs. Start with power and ground. I use copy and paste to fill in the second IC. After copying power and ground to the second IC, I add the borrow and carry outputs to the respective count down and up inputs. Then I can copy all those signals to the third IC. The first attempt at this was not brilliant, but the process improves as I go through this video. The final thing I do is align everything. I use a selection box to check the alignment and make adjustments as needed. Now I need to connect up the control signals. Initially I make a mistake and directly connect the control signals into the respective inputs without shaping the signal. I soon realize I'm going down the wrong path here and make the necessary corrections, using the code for reference. Note to self, I need to verify everything against the code to make sure it's all correct. More on that later in this video. Now I need to connect the main bus inputs and the internal module outputs. These will be used for each latch. The task is repetitive, so copy and paste is the tool to use. The final task here is to go back and make sure that the load, increment, and decrement signals are handled properly. I use all uppercase to indicate signals which are coming external to the module, and I use mixed case to indicate things that are handled internally. Because these are the same name but just different case, I'm not sure if the PCB is going to recognize those as being exactly the same signal or not. So it's something to keep an eye out when I build the PCB later. Not this video. The footprint of the logic gate ICs is separated from the actual logic gates themselves. So I'm going to spend a moment connecting power and ground since I've started to use those gates.
The next thing on the list is to connect up the latches which control the outputs for the contents LEDs. Now, it needs to be latched at the same time as everything else, so there is a clock that needs to be brought into that, but output is always on, so that's going to get tied low. The LEDs are going to get hooked up, and then of course through a resistor to ground. And that's a little bit fussy because of space constraints. So I do spend a little bit of time working on that, trying to get that all sorted out. Okay, it's time to do a little bit of cleanup. I want to draw some boxes around some of the sub assemblies here just to kind of identify what does what. I think it makes the schematic a little bit more readable. But I've also learned that when working on the PCB, it's nice to have certain nets better identified. So I'm going to spend a few minutes and actually name the nets associated with each of the LED signals so that I can keep track of that when I'm laying out the PCB. I'm setting myself up for future success here. Now, as I mentioned before, I forgot the line drivers for the control LEDs, so I have to go pull those into the schematic. I also want to take a minute and talk a little bit about a change in how I am going to display the control signals. Rather than shaping the control signals at the control logic and then risking losing them at the actual device, I'm going to display the control signal for the entire clock cycle that they are relevant. That means that I now have to have a control signal that is on or enabled for the entire clock cycle, which is fine, but it forces me into changing that I am going to shape that signal at the module itself. If something was to cause that signal to have to change for whatever reason, that shape, then that will end up forcing a redesign of the actual module. Is that a big deal? I don't believe so, because other than the clock signal forcing a latch of all the registers, everything else is combinational. I keep coming back to that. So I don't think I'm going to have a problem with that. All right, I need some room on the bottom half of this schematic, so I'm going to spend a moment and organize the logic gates that I've got wired up to their respective nets and get power and decoupling taken care of here. The next order of business is to shape the bus assert signals for each of the separate assert signals. Now these are active low signals, and the signal coming off the control logic now is going to be high, so I need to invert each one of those. There are 6 inverters on a 74HC04, so that number matches up nicely. Here I am working on the module I/O. Now, data coming in only comes in off the main bus, so that is ultimately going to be a bidirectional because I can also push data back out onto that bus. But outputs, there's 2 outputs which can assert out onto the main bus, and then I've got 4 additional buses, ALU-A, ALU-B, address bus 1, address bus 2. Plus I need something for the control signals. Now I am going to bound the clock signal by ground signals so that there is a ground coming in on either side of the clock. That's my intention. And so I'm using 16 pins wide in order to handle those signals. Prior I had 10. I'm going to end up with 4 or 5 or so that are unused, and they'll all just be tied to ground. Once the I/O is complete, it's just a matter of placing each of the latch ICs and connecting up its inputs and outputs. And I use copy and paste for this since it's a lot of repetition. The last thing to place here is power for the module. Now I'm going to go with 3 power inputs into the module. I may end up adding power to the control signals. I am not quite certain yet, but I want to make sure that I've got power on each of the 4 corners of the PCB. Why? It just feels like the right thing to do to make sure that I get good power distribution. Now I need to do a pedantic review of all of this schematic and compare it against all of the code that I've written for the emulator. I'm not going to subject you to that review on camera, but what I am going to do is I'm going to make an effort to get all of the different components named properly so that they match the variable names that I use in the code. So for that, I add an attribute to each of the placed ICs, and I am populating that with the name associated with it from the code. After that review, I'll come back and let you know if I find any issues. Okay, and I really only found 2 problems here, and they are literally in naming. This will technically work, but I have the most significant bits that are going out onto the bus on the least significant side, so I want to take a moment and swap those, and it will require swapping the names of these as well. The second is in the naming, and this is going to also impact the code. I've got LED 0 named associated with the most significant bits on the contents, and LED 1 named for the least significant bits. And that naming convention should be swapped as well. So I need to swap that both in the schematic, and I also need to swap that in the code. So after those changes in code, the contents LEDs are still displaying properly. So that's a good thing. All right, so I've got a little bit of time available. And in GitHub, I am organizing my thoughts using issues, and I'll throw a link in the description as well as at the bottom of the screen here. And of the things that I've got here that I want to take care of, one of them is really actually going to be a bug that's going to cause me some trouble. I may as well go ahead and take care of that now, and that is this break signal. The break signal itself is set up in the clock module as an active low signal right now. And I need to change that to be an active high signal, since all of my control signals coming off the control logic are all going to be active high signals. So this is going to require a change in the emulator as well as in the schematic. So let me make the change in the emulator so that that is working properly, and then we'll go and find out what changes are required in the schematic to make that work. All right, slight change plan here. I'm going to start with the schematic and identify the change that needs to be made so that I can then go back to the emulator and make that change appropriately. Ultimately, this signal is coming in as an inverted signal here into this AND gate. Really, what I need to do is I just need to invert that so it's an active high signal. And then the signal coming out of the inversion is active low going into this AND gate as it should be. I have a number of unused gates down here, and both a NAND gate as well as a NOR gate can be used as an inverter by simply tying the inputs together. So I'm going to take this NOR gate and literally insert that NOR gate in here and change this signal so that it is not inverted anymore, coming off the control logic. That should be a relatively simple change, and I'll get that done and we'll give it a test. Okay, here we go. So if I start the increment as if it's the program counter, if I now hit the break, it does drop into single step mode properly. All right, so if I hit break here, I can now step as I need to, and I can go back to run mode, and it resumes. The changes for this weren't that drastic. I did have to change the break switch to be high when pressed as opposed to high when released. Now that's not the single step, that is the switch to put us into break mode. What this is this is now the break which is coming from the control logic. The second change was to update the NOR gate that I'm using, NOR gate 4, so that it is now an input into that AND gate. The original was coming right off the A4 connection signal from the break button, which is down here at the bottom. So that's been commented out and replaced with that signal going to the NOR gate, both the A and B input of gate 4, so that it acts as an inverter. And then I had to remove the hard wires that I have in here. Let's make the changes in schematic. The hardest part of this change is actually making room for the extra gate. Doesn't take me long to get it done, but it's a little bit fussy. While I'm at it, I'm going to update the placement of the labels for the logic gates, so they sit in the middle of the gate itself rather than sitting off to the side. Okay, the last thing I want to take a look at here today are my plans for what instructions I'm going to support. down the left here, I've got the different instructions I want to be able to handle and their mnemonic that's going to be supported in the assembler. Now I've got several different addressing modes here, and you will notice that some of them are hidden. I've actually had to scale back the addressing modes that I can support. I've only got 12 bits worth of instructions, which means that I've got to keep the number of instructions within 4096. The first one I went after is the move. I've got enough that I can actually implement that in the emulator with very little work. And the different permutation of instructions that I was expecting was 624. Now, some of those just don't make sense, like moving a value from R1 into R1 simply does not make sense. So the actual implementation of that was 560 different instructions. That allowed me to reclaim 64 of those back. And so right now, the way things are lined up, I have 4,155 instructions that I am planning on supporting here. I am tracking right now to have 4,091 of those, being that I was able to reclaim 64 without issue. Now, there is one critical instruction that is missing here that I want to be able to handle if I can, and that is swap and move. Currently, I've got 60 instructions for that. If I was to have the full complement, it would be again 624 of them. Right now, I do have the swap bytes and register, so I can swap things within itself. So those would come out, it would likely be more like 560 again. All right, so I've got only 60 of those that are available to me. And that's probably going to be a bit of an issue. And so if I look at what those are likely to end up being, these are those instructions. Right now, I'm only supporting my source and destination into R1, R2, R3, and source destination of any of the I/O devices. And that's probably going to be the most used case. Ideally, I'd like to get all of the registers all the way through R12 supported. But again, that's going to be quite the number of instructions. So I'll have to take a look and see what I can reclaim here and if I can make enough room to fit any more of those instructions. Right now, I'm going to have to be very judicious about that. Is it the end of the world? No, because I can move things into a register and then I still have the swap bytes in register instruction. It just is going to take 2 instructions to perform the same operation. Here is how I am trying to map those instructions out. A lot of this is taken from the assembler as it exists now, but things like break is new, set carry, clear carry, those were sitting up here as 0E and 0F, and I like symmetry, and therefore I like the way this is shaping up. And then I can fill in these nonsensical instruction locations with some individual things and other things that can kind of fill in around all of this stuff with some of the smaller instructions. And that's what my plan is at this point. But I have all of the different moves represented here. And then near the bottom down here, I have all of the different jumps that I'm going to use represented. Now, I don't have all the hardware I need to be able to properly support everything that I've got written out here, but I've got everything set so that at least it's identified where it's going to land. This is in the GitHub repository, so if you'd like to spend some time looking at this and reviewing it more than just what's on the video here, feel free to hop out to the repository and take a look. Okay, so I feel like today's video was very productive. Now, the amount of time it took to create the schematic, that edited down quite nicely, and so for once in a very long time, I'm actually ahead of where I thought I would be. I was afraid this was going to be a very long video, and it turns out it's not quite as long as I thought it was going to be. So what's next here? Well, there's a few things that I still need to add in order to make sure that I catch up to where the build is now so that I can start retrofitting some of these changes back into the build. One of the big components that's missing at this point is the flags. And while I don't have everything built out to drive all of the flags the way they need to, I'm going to have to bite the bullet and get those flags emulating so that I can start looking for issues and making sure that I've got that sorted properly. So I'm going to make some assumptions on how I'm going to build that out, with the understanding that I may have to circle back and change those. But I am going to start tackling the flags off the ALU adder next. So that will be the next video. We'll see you soon.